Hey, so welcome to another episode of Quirkcast. Instead of doing an episode this time, this is going to be part of a new series as an attempt for us to generate material for the podcast, and also as a way to keep us rusty physicists in shape in terms of interesting recent work. So, the format is very informal. Tim's going to present uh, a few of the key findings of this very interesting topic about quantum chaos. And Mohammed and I will feel free to interject with whatever stupid questions we have.
All right. Thank you, Mikey, for the intro. And it's a pleasure to be here. And it feels like an academic presentation back in the days. But once again, this is super informal. So today I'm going to tell you a bit about how quantum systems thermalize. And do feel free to interrupt, ask any questions, and whatnot. All right. So, what exactly are we talking about? Well, the first thing is uh, you know, classical chaos is a ubiquitous phenomenon. Most of the systems in the world are complex, and as a result, it's very complicated to analyze them, and we often resort to what we call statistical physics and ultimately thermal physics to study this system. I think it's called like some kind of stadium. Like as long as so you can see these balls bouncing around in this like interesting shape. It's not a circle, nor is it a rectangle. And you can see that in the beginning, these balls are kind of a really structured pattern, right? It's balls lined up. And the longer you wait, as time goes on, it just becomes a whole mess. And eventually you have kind of like just kind of random balls in a box, right? And how do we understand this? Usually we use statistics, but then how do we justify this? And a system like these have a few typical phenomenon that I'll describe. The first one is what we call ergodicity. This is the idea that for complicated systems, and when there's no particular symmetry or particular reason for the dynamics to happen, what ends up happening is it sort of fills out the entire space. And as you can see from the animation, no matter how you start the configuration, when you can have a balls in a confined space, eventually it just kind of fills out the entire region. So that's called ergodicity, and we can define that formally. And the other thing is mixing. Basically, it means that after a while, the system seemingly kind of forgets about what happens in the past, right? Like just after a few frames of this animation on the left, you can no longer remember that. It shows no hint whatsoever that in the beginning these balls were nearby each other. There's no hint of that whatsoever. And if you just look at the animation near the end, it will be impossible for you to deduce that in the beginning these balls were really close together, right? So that's called mixing. So ergodicity and mixing, these are separate phenomenon, but ultimately in our everyday world, these come from a stronger occurrence, which is chaos. So ergodicity and mixing are both consequences of chaos. And in terms of chaos, we have a few additional phenomenon, and one is quite well known. It's called the butterfly effect, where if you just perturb the system a tiny bit, the outcomes of the systems are completely different. Like I'm sure we've all seen movies. Like imagine if someone were to go back to the past and just somehow jiggle even like a few air molecules, the entire trajectory of the history like end up being different, something like that, right? And we can formally define it as some sort of sensitivity configuration in the past, right? So all these, when these properties come together, it tells you that these properties are actually very generic for systems that we study, classical systems anyway, and we can use it to justify treating this system statistically. For example, the particles in the left, we don't have to kind of consider all the complicated dynamics, all the ways the balls bounce around each other, we can just say at the end of the day, on average, the balls are uniformly spread out in the box, something like that. Okay, so this is an extremely powerful tool that we have, at least classically. So
Sorry,
what
can I just ask a question? How
Yes.
do I reconcile this idea of mixing, where the system forgets the past, insensitive to the initial conditions, to this butterfly effect, where you describe this extreme sensitivity to the initial
Yeah,
conditions?
so mixing could happen without chaos, and usually it can. So basically, there are multiple ways it can forget about the past. There can be power laws or other less dramatic, less exponential, if I can put it that way, of forgetting of the past. And I think formally you can just look at the correlation between the particles, right? You can look at the correlation of the position of the two particles as a function of the initial position. And as time goes on, when a system mixes, that correlation will be smaller and smaller. That means it's harder to predict what happens next. The chaos, it takes it to the extreme form where this correlation gets small, but small in a very quick way. It goes more exponentially. So exponential is usually much more powerful than like a power law, let's say. So chaos has mixing. It's a particular strong form of mixing, and I think the butterfly effect particularly requires an exponential level of sensitivity. Does that answer your question?
Yeah, I think so. I'm just confused about like the system forgetting the past versus the system being exponentially sensitive to the past. Is it like what you're saying is that although the system forgets the initial configuration, a small change in the initial configuration leads to a drastically large difference in the densities in a certain region, for example?
Yeah, I think I'm using the two terms interchangeably. Like I'm not being too precise. Like I suppose there could be some difference, but I think what I say is the same thing. Forgetting the past is the same thing as some hyper sensitivity of the past, basically. But for chaos, it's just very particular. It has to be exponential, basically.
Is it the necessary condition, but not the sufficient ones, or like so? Because you could find a lot of systems that have a mixing situation in it or a good acidity, but they're not necessarily a chaos situation.
Right. Yeah, there are systems that are ergodic and they mix, and they're not chaotic. You can cook that up mathematically, but I think most system in our everyday world is chaotic in that way.
Yeah, but you're saying that if it's chaotic, then it's definitely has the mixing and ergodicity.
Yeah, I think that's true. Yeah, I think that's true. I don't know the formal definition of chaos, but I think usually it involves ergodicity and mixing. Yeah. So chaos implies ergodicity and mixing, I believe. Right. So, anyway, technicalities aside, I mean the focus of this is not classical chaos. Classical case. Let me just add one fact. So if a system is chaotic, you can kind of prove that there's this thing called thermalization, and that it's exactly the same thing I described, where you can treat the system as if it's random, and you can use statistics to approximate the system, and say that the system has been thermalized. Right. So that's the key point that I want to get across. Right. So we use chaos as an excuse to show that things thermalize, and in such a way that we can use thermal physics to describe the system. Okay.
I have a questions about this. I mean, I have to my knowledge is rusty, but
sure.
as far as I remember, if you have for example, if you pick an observable of a system, then thermalization was when the expectation values of that observable would actually over time reaches to the, for example, microcanonical expectation value that you expected from that, independent if the system is chaotic or not.
I think that's a more nuanced level of description. I think we'll get to that. I think we'll get to something like that. But yeah. But technically, yeah, that's closer to the truth, I think. But anyway, let me keep going and see if I answer your question later on. All right. So what is the problem here? The problem is that the world, unfortunately, is quantum mechanical. And so all this classical thermalization only works in the classical sense. And you can ask the question, well, what does it matter? Why does quantum mechanics mess up our discussion? Well, to show you some examples, these are so in quantum physics, particles, the way we describe particles are through waves. So instead of thinking of billiards bouncing back and forth, we have these quantum waves kind of sloshing around in this cavity, in this pill-shaped cavity that I was showing you before. And these are some of the waves that you can solve using differential equations. And you can see that there's a pattern, it seems like. It doesn't really look chaotic in any way. So it really raises the question, like, does ergodicity still apply? What about mixing? And what about the butterfly effect? Like, where is it? Right? So all the stuff we know about classical physics kind of goes out of the window a little bit. It's not obvious, right? And it's not even obvious how we define chaos in this situation, because we just have some waves sloshing around, and some of these solutions for these waves seem quite orderly. Like, there's no like crazy mixing around, and these are in fact standing waves, or eigenstates as we like to call it. So what gives, right? So this is really the central question. Without chaos, how do quantum systems thermalize, right?
I have a question, but I mean, in a classical system, if you have, assuming that you have a wave, like a liquid or something in a Navier-Stokes formula or something. So we would be able to define chaos like more accurately, I assume, than quantum mechanics. So what makes a difference between, like you mentioned that in quantum mechanics we use the waves, so that complicates the situation, but we have examples of like classical waves as well. Is it because of the uncertainty principles that you can messes up the things, like the situations, or this kind of, like, you don't have a kind of trajectories that we have in classical mechanics, that you can have a defined trajectory similar to that in quantum mechanics? Is like it's obscure.
Yeah, what you mentioned is great. So in fact that's going to be the next slide. So what you mentioned is exactly correct. So of course, like you said, you can easily counter my point. You're like, hey Tim, like literally classical mechanics comes from quantum mechanics. Like you could literally think of balls as like concentrated waves, and you could reuse the classical chaos and derive thermalization, right? That's certainly doable, right? So why are we talking about this? But it turns out that if you look at experiments, it like there are purely quantum mechanical systems that thermalize, and it does not have to go through classical physics. So even though this derivation seems like it's possible, this cannot be the only way where quantum system go to thermal system, go into thermal physics. And in fact, I think in many cases we see an even stronger form of thermalization, because going through classical chaos, the balls have to move around, it has to mix well enough. There are many steps to chaos, and a lot of times systems, there's not enough time for them to do that, right? But yet some of these systems still exhibit these thermalization behavior, right? And of course, you can also tell me like, hey, look, Tim, I've studied like graduate level physics. We study quantum mechanics, we study thermal physics, and there's definitely quantum statistical mechanics, right? Like it works. But if you think a little harder, quantum statistical mechanics involves a little bit of classical mechanics, because usually you assume there's a quantum system and it's interacting with what we call a thermal bath. There's some sort of temperature, and that bath, we treat it classically. And when that happens, when quantum system is mixing with like some classical noise, of course you get thermal physics again, right? But what we're really after is this direct route. Imagine the entire world that we have is really just a quantum system, right? There's nothing classical about it. Classical physics is just an approximation, and in fact we see purely quantum mechanical system with that doesn't really behave classically still have some of these thermal statistical behavior. The question is, how do quantum physics directly go to thermal physics? Like where does the temperature emerge, right? Like imagine I have a quantum system interacting with a bath. I mean, the bath is also quantum mechanical. Why can we describe it with a temperature? And as a matter of fact, there are many systems without a thermal bath. Like for example, a nucleon, right? Like inside a nucleon, let's say really heavy nucleons like iron or lead or whatever. Inside the nucleons, the neutrons and protons are very quantum mechanical, and there are many of them, and you can kind of derive some sort of statistical behavior and quantum statistical mechanical behavior inside that atom, but that atom is completely isolated from its surrounding, right? So where does the temperature of the nucleon come from, right? So these are the essential questions. So sure, you can go from quantum to classical to thermal, but something's missing here. There must be a direct link from quantum mechanics straight to thermal physics, right? So does that answer your question or your viewpoint, Mohammed?
Yeah, this is very good. I didn't know, honestly, there is, because whenever we learn quantum mechanics, you always have this, at least in the different interpretation exists, but you always have this observer, and the observer is a classical and makes measurements on some quantum board. But assuming that there's no reservoir that is classical with the defined temperature that we set it there, how we want actually to understand where the temperature comes or this thermal physics comes from in a quantum world. So this is very exciting.
Yeah, exactly. Yeah. So that's the point. And in fact, these will become super important in fields such as quantum computing, where we're manipulating many really small quantum system, and there's certainly thermal behaviors, and black hole physics, where we believe quantum gravity will ultimately lead to something like a temperature, and none of it is classical. So it's a very important concept to get through. All right. So where does this begin? A little bit of historical context. Okay.
Can I just ask a question? So in
Yes.
the previous in your picture with the ordered waves,
Yes.
if I think about college quantum mechanics, that order arises because of the symmetry of the boundary conditions, right?
Oh, you mean the fancy picture with the. You mean these?
Yeah.
Yeah. It depends on the boundary conditions. Yeah. But the point is,
Do you observe quantum chaos even in these kinds of really symmetric setups?
yes,
Well, I guess the nucleon example is.
that actually is the point. And the point we're going to get to is called the eigenstate thermalization. It's telling you that even an eigenstate, these individual standing wave-like configuration, there is a notion in which we can think of them as being in quantum chaos. That's sort of the important part. So yes, even these configuration, we can think of them as exhibiting quantum chaos, ultimately. So we're hoping to get to that, right? Okay, so the beginning of this, really the meat of this presentation is Wigner's brilliant idea. So what exactly is the issue? So back in the days, as I alluded to, we have a lot of heavy nuclei, and heavy nuclei are heavily quantum mechanical. They're highly quantum mechanical systems, and one thing we want to do is we want to predict kind of the mass of these nucleons, or given that mass equals E equals mc squared, or the energy levels, right? So it's a very basic kind of calculation, if you like, or vanilla calculation to calculate these what we call the energy eigenstate for these systems. So people try for a long time, but but it's very complicated, as you can imagine, these heavy nuclei, and they couldn't really quite make a lot of sense out of the patterns of these energy levels, right? So there was a big push to try to understand like what's up with that. But then Wigner comes along, Wigner Eugene, a Nobel laureate, and he had the idea that he had the idea that instead of really studying the details of these energy levels, let's study the statistics of these energy levels. So basically, instead of studying like a individual nuclei, like I don't know, lead or iron, let's aggregate all possible nuclei and look at the what we call sort of the energy gaps between levels. So for example, if I have 1,000 energy levels, let's look at the energy difference between level 1,000 and 1,001, 1,001 and 1,002. Okay. And then imagine if you were to make a plot in this figure in the presentation. If you make a histogram, it turns out that if you stack over 1,726 spacings, they form like a reasonably smooth curve. And it turns out Wigner was able to predict what that shape looks like using random matrix, right? The idea is that, hey, if these interactions are so complicated, there must be some statistics behind it. So instead of studying these interactions precisely, let's pretend that they're just random matrices and see for these random matrices what are the properties of these energies. And he was able to predict statistically the spacings of these energy levels, and pretty well too. And that kind of sparked a whole new idea. The idea is, instead of thinking about, kind of in a classical way where trajectories move around, or maybe let me go further, like observables themselves, right? And let me explain this plot a little bit with a little more technical detail. So the GOE, I think it's the Gaussian orthonormal ensemble average. It's just saying that, hey, pretend that these are random matrices. And the reason why there's a Poisson distribution here, which is basically just an exponential here, is that people predict that for what we call integrable models, the spacing should behave in a Poisson way. But details aside, it shows that heavy nuclei are not integrable. They don't obey the Poisson statistics. They obey the Gaussian random matrix ensemble. Okay, so now, so Wigner's idea is not fully fleshed out, basically. Like, random matrices are definitely not 100% the way to go, because interactions are not really random, right? There's some structure in them. Certainly, there's some component you can think of as random, but minimally, this gives us a path forward, how to think about quantum chaos, how to use classical chaos analogies and bring it to the quantum realm. So like I mentioned before, in the classical sense, you have particles moving around and they follow these random trajectories. Okay. Now, in the quantum realm, instead of thinking about those as random, of course, quantum already has quantum uncertainty, so there's uncertainty in these paths. But we have an additional level of randomness. We should think of the interactions or observables later on as random matrices. We should think of the Hamiltonian kind of like as some sort of random assortment of interactions. And then if you assume that you can go a little further. In the classical situation, we see the billiards filling up the region, right? The quantum analog is more abstract. In the quantum analog, we have these states called eigenstates, and we have these abstract notion where these states live. They are Hilbert space, and you can show that if you assume random matrices, the eigenvectors will fill the Hilbert space. And the butterfly effect, this extreme sensitivity to initial conditions, you can formalize it actually in a quantum realm. You can look at operators. This is rather technical, and you can look at the exponential growth of certain operators, or really what we call out of time commutators, right? But I won't go into too much detail here. So it seems like there is a path to quantum chaos now, right? But it's not totally fleshed out. But let's see what happens if we bring these ideas forward, right? Okay.
Tim, one question I have is
Yes.
this. So when we talk about random matrices, we're still looking at like classical probability distributions, but used in a different way. So this, would you say this isn't like the absolute path there? It's still, instead of using like classical mechanics, it now uses like classical probability theory as
Yeah.
like kind of another approximation, but closer to quantum thermalization.
Yeah, basically. But this is not relying on any classical physics, right? This is relying on classical probability. And let me remind everyone that there is still quantum uncertainty. You know, we're not removing the uncertainty principle. This is on top of the uncertainty principle. But in addition to that, we're quantifying our ignorance, basically, right? We're saying that, hey, we are ignorant of the complicated interactions, so we're going to approximate it using classical probability theory, and because quantum physics is governed by matrices, we're going to use random matrix theories, right? And this turns out it will actually get us closer to thermalization, right? And maybe
Tim, one more question. This is kind of like a very meta question, but
yes.
how would you like be able to characterize your uncertainty of your uncertainty? Because you're estimating some kind of models, and those models have parameters, and those parameters have uncertainty around them. There's kind of like, do you see like priors being invoked, or is it just like, yeah, just how do you like know this is like a good fit? Because these distributions are arbitrary.
Yeah, so theoretically, people can run numerical simulations. Those are quite complicated, but these are just matrices, right? You can throw it in a computer and run it, and it turns out that it does, what I'm going to propose does make sense. It does match the prediction. You can pretend that things are random matrices, and people have also built like atomic experiments. You can also show that this is true. So I hope that answers the question somewhat, because ultimately the final arbiter is experiment, because this is physics. So yeah. So it doesn't always work.
Yeah, fair.
I think this will be made clear with this thought experiment that I cooked up for you guys, right? Okay. So how do we think about this? And keep in mind that this is active research. Like, there's no proof or anything. But my emphasis is on how do we think about this, right? So first, let's go back to our let us go back to our system. So imagine in the same vein, we have this pill shaped object, and instead of having billiards, we have a quantum mechanical particle inside this pill shaped box, and these are simulations on what happens if you evolve this quantum mechanical wave. Okay, and this is one pattern that you might see, right? The ball moves to the left and it kind of diffuses out and all that. Okay, so how do we think about thermalization? Okay, well, the way we think about thermalization is we have to look at observable by observable, and clearly not all observable thermalizes. And if you just look at the energy, the energy doesn't necessarily have to thermalize, right? If a system has a particular energy, it might just have a particular energy, especially quantum mechanically. So in order to think about thermalization, we should look at thermalization one bit at a time. So what do I mean by observable? I mean if I try to measure, let's say in this red circle, the content inside that red circle, let's look at the average energy of this blob, right? Because the average energy of the whole thing is conserved, so there's no sense in which it will change to some extent. But if I look at this tiny region and study its property, it seems like things are going to change. And what I might observe is something like this, right? Initially, you might have something that's super, some random some values depending on my initial conditions, and it could fluctuate back and forth, as the waves coming in, crashing in, back and forth, right? And at some point, it's gonna settle down to some value, and this is from observations or simulations, right? And this green dotted line, you can think of it as some sort of statistical mechanics average with some temperature. And temperature here has to be an emergent quantity, because there's no temperature we started with. It's just a ball in some cavity, right? So there basically is a temperature induced by the surrounding this little red circle, right? And after you settle down, you can say that it sort of has thermalized, and then from time to time it will fluctuate around a little bit from this value, but we can think of them as thermal noise. And this goes back to Muhammad's comment. Like this is probably a more sophisticated way of defining what thermalization means, because we don't really have a good idea really what thermalization is, but I think that goes back to your point. So with that in mind, yeah.
Tim, one question for you. How is thermalize mean like reached equilibrium, or what is like a definition I can hold for thermalize?
So good point. That's what we're trying to get to. Like I'm intentionally trying to be vague, because we don't really have a definition for what it means for a quantum system to thermalize, basically. Because in classically, it thermalizes when there's chaos and everything mixed together, and then we can say it has been thermalized because it forgets about the past, right? But in quantum system, like, what the hell is thermalization, right? So we're trying to define it right now. So the definition through this discussion is, we can say that an observable is thermalized if the observable itself becomes some sort of thermalized average plus random noise. So that's the definition we're trying to get at, right? And it's not
for quantum systems. Are we guaranteed that the line is eventually going to reverse and go back to its behavior at the beginning of that wiggle?
No, well, okay. So observables, so on an observable by observable basis, okay, like you might be able to cook up an observable that does that, but for a generic observable, chances are it won't, basically. So there's some level of genericity. I don't know if that's a word. Does that make sense? Like
if I wait an infinite amount of time, since these are all waves, everything's periodic, and it'll eventually revisit the state. Right?
Wait, hold on. The thing is, it's not periodic though. Like the system isn't necessarily periodic.
Are you saying it's also not ergodic as well?
Well, it's not clear what ergodic means. So, okay, let me say, I take that back. So the wave function is periodic in some ways. Like you can look at you can look at the if you look at eigenstate, right? There's some fluctuation back and forth. But I'm not talking about the eigenstate. I'm talking about a particular observable, right? Yes. So the state can be periodic, but the observable is not, because basically the observable is in some sense incommensurate with the state. It doesn't care much about the state, right? Does that make sense? Like there's no, like you haven't designed an observable that is somehow designed for a particular state. So you wouldn't see this periodic behavior, even though the state might be periodic. Does that make sense in some way? I guess it's a bit vague. So yeah. So in this way, let me just go to the eigenvalue thermalization hypothesis, right? And once again, this is the hypothesis. There's no like concrete proof or anything. It was proposed by Mark Schernicki. I forgot the year, 94, I think, right? So it's just a definition, a proposal for what it means for a quantum system to thermalize, and it turns out to be very accurate for many observables and for many systems, and that's what it is. Right? I hope that answers some questions, clarify a little bit. All right. Okay. So this presentation is really focused on intuition. So I really want to go and dig into this detail, dig into like what exactly does that mean, right? Because in a lot of papers you just see the equations, but like where's the intuition, right? So when we say something is in thermal equilibrium, I guess in a quantum mechanical sense, we're saying that an observable is equals to some average plus some random noise. So what exactly does that mean? there's actually an equation behind it. There's a little equation behind it, but I don't want to focus too much on the equation. I want to focus on the intuition. So the equation is on an operator level, and in quantum mechanics, every observable is described by an operator. We're saying that we can pretend an operator equals to some average plus random. That's what the Eigenstate Thermalization Hypothesis means. It's on an observable by observable basis, right? So the observable, first of all, it's not every observable. Some observable will thermalize according to the ETH, Eigenstate Thermalization Hypothesis. Some might not. And the observable has to be small. It cannot cover the whole system. For example, if you talk about if the observable is, let's say, the energy of the entire system, it's not going to obey this, right? Okay, and it has to be small, generally less than half of the system. I think from simulations and studies, it should be less than half of the system, and it has to be local. So you can't just cook up some really contrived observable, and like Mikey described, in such a way that it has these weird behavior. It has to be local enough, like a sensible observable, like for example, like the energy of two particles in a small region of your experiment, for example, or some spin in a spin chain on a particular location, right? So those are usually the observables that we talk about, and it's not obvious which observables obey this and which do not, right? And another thing is, when we say equal, we don't mean equal, because on the left hand side you have something that's concrete, and on the right hand side you have something that is a statistical random thing. Like on the left hand side you have something that's not stochastic, on the right hand side you have something that's stochastic. So it can't possibly be equal, right? But we're only saying that they're equal approximately in some statistical sense, right? So this equation might not work if you're only looking at one observable in one state. That might not work. You have to look at one observable in many different states. Then you see that it obeys this behavior. And also there could be sub-leading order corrections, right? Okay. And the average, the important thing is it's a smooth function, right? Why is that important? Because even states in quantum physics, even states with the same energy can have drastically different observable, right? Let's say one state has energy 100 and the state has energy 101. It's not necessarily true that these states are similar. There's no guarantee in quantum physics, right? They could be very different. But the point is, when things thermalize, all these differences get smoothed out, basically, and it becomes a smoothed over average. And hidden inside this definition of this smooth average is some sort of ensemble. This means that there's from here it effectively defines a temperature. It's a bit hidden in there, but Mohammed, you were talking about microcanonical ensemble, which is a tool we use in statistical physics. It's hidden in there, basically. When you say when you say there's some average, this average will agree with your statistical mechanics calculations. And the point is, yes.
Just one question. So as far as I remember, when you have an observable, you could also expand it in terms of their eigenstate. And there was sometimes the system, like you would be able, one of those eigenstate, for example, would be the eigenstate of that systems, and with some probabilities plus whatever that you would have. You recall these expansions between, like, in terms of the eigenstate. Are you saying that this average would be the average over the system that, like the random part depends on the energy and the time, and over time is like probably like disappears?
No. It does not depend on time. So the point is that this is an operator level statement. There's no time dependency, right? And it's okay. stating that if you study properties, like if you study properties of an operator over multiple eigenstates, you can kind of smooth it out in some ways and describe it statistically. Later on I'll show some plot and it will make a little more sense, right? So this is not an average over time. or an average over noise or whatever. It's that if you look like going back to Wigner's proposal, like it's when you look at these quantum systems and look at multiple and many thousands of energy levels, right? Maybe many similar system, and you look at you aggregate all those and you look at the statistical behavior, and this emerges. Not sure if that make too much sense, but it's an option.
Can I think about this in the simplest example? If I just have like a particle in a box, then it'll if there's a certain number of modes in the box, it'll time evolve with some periodic. The state will evolve periodically. And if this chaos arises from the observable being local, can I think of that as like a projection of the state onto? Can I think of it as being the result of the projection of the state onto a limited subspace of the Hilbert space, or
yeah, exactly. Yeah, basically, when you look at a suitable observable, you're not observing the whole system. You're observing kind of like a random selection of a subsystem. And because the subsystem doesn't care too much about the setup of the whole system, that's why you can look at these averages. It effectively, you're kind of like just randomly selecting out a subsystem, and that doesn't care of your particular setup. So that's why it looks kind of like smoothed out in some ways, right?
Got it. That makes sense.
So that's the whole point, yeah. And of course, yeah. And of course, there's some random residual, and you can think of that as thermal noise, kind of, but it's not thermal noise. It's basically the statement that when you have a quantum chaotic system, all your eigenstate kind of become random vectors, right? So that's why you can think of these residual terms as these random ups and downs. Like for example, if you pick a particular eigenstate, this formula may not work very well, but it will be a small noise. It will only happen rarely, right? So this piece is telling you about that. It's the little fluctuation that will average to zero ultimately. And these if you want to be more precise, the average term is only on the diagonal matrix element, and the random governs both the diagonal and the off diagonal. So it governs the interference terms, and generally the interference terms is very small, so that so that quantum behavior becomes becomes subdominant. But of course, you can test this hypothesis in smaller and smaller system, where you see this random noise. Right?
So you mentioned this randomness is that diagonal, off diagonal, like sandwiches for this observable, right?
Basically.
So if there is any degeneracy or something, then that's not gonna over time to reduce to zero, or like this randomness, right?
Yeah, it won't reduce to zero, but it will average to zero if you look at many different eigenstates.
Even with degeneracy?
Degeneracy. Oh yeah, when you have degeneracy, usually you think you need to think of them as a symmetry. Then you just say the noise also has to obey that symmetry. Then this whole thing will apply. So for example, for some condensed matter system, you might have some degeneracy, and that might be because of time reversal symmetry, right? Then your random matrix, as opposed to being Hermitian, it might just be real, or it would just be a different class of random matrices. I wonder if that makes sense. That's usually how degeneracies are dealt with. But I think small amount of accidental degeneracy is usually okay. Right. Yeah. So anyway, this is near the end of my talk. I just want to show a little bit of application, and there are many papers that try to test out this hypothesis. And once again, this is just a hypothesis. I'm just trying to give you some intuition. And it has been proved actually for integrable system. If you look at an integrable system and you add something that's not integrable, you can prove that the end result is that in some class of observables will obey the Eigenstate Thermalization Hypothesis. And this is a paper by some Princeton folks, I think David Hughes' team. And it's a numerical calculation, and it shows exactly what I mean. So these are, it's a little hard to read this plot, but you can look at this figure, right? This is basically the average, it's so it looks at a particular system, and it looks at let's say some observable. You can see this some spin x, right? It's a spin chain, yeah. And just look at this observable over many thousands of eigenstates with different parameters and whatnot, and it looks at, and you see that on average it follows this kind of this linear line, right, which is the thermal average. And if you look at particular eigenstate, it might not obey this line. But then there's this noise, right? If you look at nearby eigenstates, eventually this noise kind of average out. And there are different levels of noise too, depending on your system, right? And you can think of that as, I don't know, some sort of, I'm not sure if you can think of that as temperature or whatnot, but the noise can vary. But ultimately, it shows a universal behavior where these kind of go toward the same function. Just like Wigner's, but it is basically a generalization of Wigner's proposal using random matrices to study these observables. And they tested on many different systems numerically. And I think, question? Yeah.
It surprises me that nobody has done this, because this is just a simple expansion, and then you would say that, okay, now that you want to formulate this, you would use a random matrix theory similar to what Wigner had done, and then you would have like gotten to the thermalization. It's just surprises me.
Yeah, it feels like it should be in Griffith's textbook, right?
Yeah, it feels like it should.
I mean, this should have been like, I mean, you would think that this would have been resolved long ago, and it just surprises me. There are things that I don't know why people like dig string theory, and there are so many problems hanging around that I don't know. It just seems like very straightforward computation to me that would have done, and then to formulate this with a random matrix theory is just. Yeah, I have no idea why not.
Yeah.
Is it just because quantum physicists don't care about chaos typically? Or haven't historically?
Maybe.
I think so. I think it feels like, I think a lot of people just think that, hey, maybe it's so obvious that nobody bothered to really formalize it. But once you formalize it, there's actually interesting physics that comes out. I mean, okay, I think the thermalization hypothesis, like, it's not all that fancy, right? Like if you break it down, it's an equation that has some random matrix theory in it. But I think what's surprising is what you can do with it, right? Like not only can you run simulation and prove it, validate it, you can actually use it for calculation. So there have been calculations, for example, to put bounds on chaos. You can actually derive the upper bound on the exponential of the butterfly effect, and you can actually try to use it to look at quantum computing error correction. You know, how do you, because when you have a lot of qubits, there's some sense in which the system could also thermalize. And you can also use this to help you understand black hole physics, because ultimately black holes gives rise to Hawking radiation, so we know that quantum system can thermalize to some extent. So you can use this ansatz, this hypothesis, to derive some properties of black holes. So I think the application is what's interesting.
You showed some like some motion, some like it was something very interesting that was moving, like a ball bouncing. It could be like a system of like a black holes in a like, or like something like that to see how it thermalizes, like by this kind of calculation. They're working on something like that.
I know people have worked on black holes to see,
like a binary black hole, for example. I don't know.
No,
it thermalizes.
No, people definitely have studied black holes, and one interesting result was that black holes are the most chaotic object in the universe. Basically, you can calculate the butterfly effect, the exponent of the black hole, and it goes like some 2 pi divided by the temperature, something like that, right? And you can show that that's the largest exponential possible. So basically, black holes are amazing scrambler. It's the best. It's a system with the greatest level of butterfly effect. So people have calculated things like this, exactly like you said. Like look at like a look at a black hole and a white hole combined.
Which you could expect this black hole. So yes, to have.
Yeah, so very interesting results.
Situation.
Yeah, very interesting results.
Very cool.
Hey, Tim, one question that I have is around like now that you bring in noise into this, into the saying the observe the observable is equal to some average plus randomness. What does that randomness actually mean, or is there like a interpretation around it?
Yeah, so that's super interesting. I'm glad that you asked this question. Because usually when you say something is random, like there's a source of randomness, right? Like either it's an inherent randomness, or it's a randomness due to ignorance, right?
Can you explain what that means?
Right. Yeah.
Randomness versus
Yeah. For example, like, well, I guess actually, well, okay, like there's probably isn't true randomness, right? Like the closest thing we have is quantum physics. Like quantum mechanics has some level of inherent randomness. Like if you look at a radioactive decay, you can never know when the atom will decay. That just is, it's just quantum mechanically random, so you cannot predict. But if you look at things like the stock market moves ups and down. Like it seems like it's impossible to predict, but ultimately the price of the stock market has to do with just people placing bids and buying stock and selling stock. Like technically, if you take into the actions of the emotions and the actions of everyone in the world, you could predict stock prices, right? But it's just so impractical.
Wait, hold on. I want to challenge that slightly. Well, because it assumes you can come up with some countable way of describing how emotions would contribute to people's decision whether to buy or sell. There would also be the whole complexity of the network itself, that it may have certain properties. Yeah.
Right, sure. But let's remove that. Let's just say, like, imagine you have a toy stock and everyone just clicks buttons to buy and sell. And I guess if you ask everyone to click at a certain way, then you can use that to predict the stock movement.
Oh, I see. So more of like deterministic systems with a lot of agents in them. Is that kind of what you mean?
Yeah,
Gotcha.
So I think that's the closest analog for this for the situation here, because these like in these plots on the right, like the quantum nature of the system is just totally removed. It's like pretending you are just perfect, like removing all the quantum noise. It's just looking at the property of the quantum system, and even then there is these fluctuations from the average, right? And you can see there's some exceptional fluctuations. As a matter of fact, if you look at around the first plot, like negative point half, like 0.05, right? Okay, so these are seemingly due to our ignorance of the system, because we're using some really contrived this Eigenstate Thermalization Hypothesis to approximate it. That's why we're missing these details. But I mean, of course, but these are computer simulations, right? Of course, you can kind of flip the script a little bit. Like, what about in the real world, right? When you measure these things, is it plausible that there just is noise on the interaction? Like, is it possible that the world we observe really is just some average of it's some statistical average of some interactions that we don't yet know what those are? And you can argue that maybe like quantum field theory is something like that. So basically, I have no comment on that. I don't I don't know what the right answer is. It feels like it's just our ignorance, but maybe in some weird way we should think about our universe as some average of some like interaction strength or whatever. I don't know if that makes sense.
Well, are you, so let me see if I can understand this. Are you saying like what we can count references some sort of average, and even if you use a distribution, that distribution itself is some kind of, really loosely speaking, like an average of some greater amount of ignorance that it's like unknowable.
Yeah, exactly. Like especially when we look at quantum field theory, right? Like we measure, let's say we measure the mass of the Higgs boson, whatever, some parameters, right? like, is it really the mass, or is it the average of some of these, like some of these properties, right? These wigglings, but you average it out and you get the mass of the Higgs boson, right? I don't think we know, it's not obvious that these parameters are really fundamental parameters versus just some smoothed out average of something that's more fundamental. Or maybe there is nothing more fundamental. Maybe like ignorance of the system is inherent and we have to deal with it. So yeah, I think
And-
this yeah.
Oh, so one more question. So one thing I'm curious about is like, it seems like there's some notion of equilibrium. What about like non-equilibrium situations that seem like they have equilibrium in the short term, but in the long term, they like, it's not as stable.
Yeah, I
Kind of
think
like the solar system equivalent.
yeah, I think definitely you can probably generalize the eigenstate thermalization hypothesis with some additional slow time dependence. I think that's certainly reasonable. You can just add a time dependence to that. And yeah, and probably that's in fact that's probably how the world works. like eigenstate thermalization hypothesis, it's more general than ordinary like chaos, like the way we understand chaos theory. It's more general. It's more correct. Basically, we've tested on quantum system, and you can prove that the eigenstate thermalization hypothesis leads to classical thermalization. You can prove that. So yeah, I think this is a better way of thinking about the world, probably, at least for now.
Hey, sorry guys, since it's informal, I gotta take off.
Okay.
But that was really awesome, Tim. Thanks. You really put
Yeah.
a high bar.
All right. Well, to our listeners, I guess, yeah, that's
Thank
it
you
for
so
the
much,
talk.
Tim.
Yeah. All right.
Yeah, thank you, Tim. This was wonderful.
All right. Yeah. Thank you for joining.
Really good.
Bye, guys.
Yeah.
Have a good night, guys.
See you guys.
Bye.
Bye.